In this video, we discuss principal component analysis, PCA, an algorithm for linear dimensionality reduction. PCA was first proposed by Pearson and Hotelling, who's been around for over 100 years. It's still one of the most commonly used techniques for data compression and data visualization. It's also used for identification of simple patterns, latent factors, and structures in highly dimensional data. We aim to derive PCA from first principles, making use of what we know about basis change, projections, eigenvalues, Gaussian distribution, and constraint optimization. Working directly with high-dimensional data, such as images, comes with some difficulties. It's hard to analyze, interpretation is difficult, and visualization is nearly impossible. From a practical standpoint, storage of data vectors can also be expensive. However, high-dimensional data often has properties that we can exploit. For example, high-dimensional data is often overcomplete. That is, many dimensions are redundant and can be explained by a combination of other dimensions. Furthermore, dimensions in highly dimensional data are often correlated so that the data possesses an intrinsic lower dimensional structure. Dimensionality reduction exploits structure and correlation and allows us to work with more compact representation of the data, ideally without losing any information. We can think of dimensionality reduction as a compression technique similar to JPEG or MP3, which are compression algorithms for images and music. In principal component analysis, we are interested in finding projections, y tilde n, of data points, xn, that are similar to the original data points as possible, but which have a significantly lower intrinsic dimensionality. Dimensionality reduction generally exploits a property of high-dimensional data, that it often lies on a lower dimensional subspace. The figure here gives an illustration of what we mean in 2 dimensions. Although the data on the left panel does not quite lie on the line, the data does not vary much in the x2 direction, so we can express it as if it was on the line. In doing so, while we have loss, we have very little loss. To describe the data in the right panel, we only need the x1 coordinate, and so the data lies in the one-dimensional subspace of R2. Consider an IID dataset X consisting of vectors x1 through xn, where each of those vectors is d-dimensional with mean 0, that possess the data covariance matrix S equals 1 over n times the sum of xn transpose. Furthermore, we assume there exists a low-dimensional compressed representation, Zn of xn, where Zn is equal to B transpose xn, and that's in Rm, where we define the projection matrix B to be the vector B1 through Bm, each of d-dimensional vectors. Assume the columns of B are orthonormal, so that Bi transpose Bj equals 0 if and only if I is different from j, and Bi transpose Bi is equal to 1. We seek an m-dimensional subspace U of Rd, where the dimension of U is equal to m, which is less than d, onto which we project the data. We denote the projected data by xn tilde in U, and their coordinates with respect to the basis vectors b1 through bm of U by Zn. Our aim is to find projections xn tilde in Rd, or equivalently the codes Zn and their basis vectors b1 through bm, so that they are as similar to the original data, xn, as possible, and as such, we minimize the loss due to compression. Consider R2 with the canonical basis E1 is equal to 1, 0, and E2 equals 0, 1. We know that any x in R2 can be represented as a linear combination of these basis vectors. For example, the vector 6, 2 can be represented as 6e1 plus 2e2. However, when we consider vectors of the form x tilde equals 0, z, those can also be represented in the form 0 times e1 plus z times e2. However, by doing this, we only need to remember the z value. The dimension of the vector space corresponds to the number of the basis vectors. In this case, we've got it down to one basis vector. More precisely, the set x tilde of vectors with the standard vector addition, scalar multiplication forms a vector subspace U with the dimension of U is equal to 1 because U is equal to the span of E2. In principal component analysis, we find a compressed version Z of the original data X. The compressed data can be reconstructed into X tilde, which lives in the original data space but has an intrinsically lower dimensional reduction than X. In our next video, we'll use the maximum variance perspective to talk more about principal component analysis.